In this video, we're going to transition back from spring break by looking at sections 4.2, 4.3, and 4.4. This is a variety of ideas related to the function, its first derivative, its second derivative. We're going to introduce some new words eventually in following videos about critical points and inflection points. I just want to help everybody remember that if we've had a function f of t, where did we come from at the beginning of class? Perhaps this function was given to you. There was this thing that we defined called f prime at t, which is the first derivative of the function, and we computed it by looking at a limit as h goes to 0, the function evaluated at t plus h minus the function evaluated at t divided by h. All right, and that's what we called the first derivative. And we knew, for example, we've developed some shortcuts that if the function f of t was equal to t squared, then there was this thing called the power rule, and we know that f prime at t, if we actually did that limit, the derivative would come out to be 2t. Okay? And we know that because the derivative is also a function, that we could probably do the power rule again on that function and find something called f double prime of t, which is the derivative of the first derivative. So if you just keep taking another derivative, then you would have the derivative of 2t, and that would come out to be equal to 2, right? So one of the ideas here is that if you want to look at f double prime at t, we could actually do a limit as h goes to 0, but it would be the derivative evaluated at t plus h minus the derivative evaluated at t divided by h. So if, for example, you knew that f prime at t was equal to 2t, then you could do 2 times t plus h, just using the new function, using the derivative, minus the function f prime at t, which would be 2t divided by h. And then we could actually try to compute this limit. This would be the limit as h goes to 0, 2t plus 2h minus 2t over h. A lot of algebra cancellation would happen. You'd get the two t's canceling. You would get the limit as h goes to 0, 2h over h, which is 0 over 0, but some nice algebra happens. The two h's cancel out, and we get the limit as h goes to 0 of 2, which is equal to 2, which is the same answer we got from the shortcut. So you'll recall that this is where we've come from. We know how to take first and second derivatives, and we're recalling the limit definition of the derivative. Okay, so one thing I wanted to do is to just help us transition. I want to help us transition back, okay, by looking at the variety of different ways that we can look at derivatives. We can look at derivatives numerically, with a bunch of numbers, for example. We can look at limits graphically. And then we know that there are just another way just to look at the formulas as we have done above. Okay. So in the rest of this video, we're just going to just kind of look at some tables of values and just kind of match those back up with the graphs and the pictures. Okay. So here we have on this page, we can see that as promised, that there is a function given to us. That'll be the function right here, function f of t. In this case, we're going to start with t squared, okay? And we just showed a second ago from the power rule that f prime at t was equal to 2t. And then we did that limit, we did the limit to find f double prime at t, and we got that was equal to 2. So what we're seeing here is three different graphs. Here is the graph of f double prime. Here is the graph red of f prime, and then the graph in blue is the function itself. And just to kind of help transition, here is to the right over here a table of values I've just created for different values of t. 0.5, 1, 1.5. So this is h is equal to 0.5. We've got different spacings for t. we've got the function f of t column here, and then remembering some terminology called the average rate of change, this is kind of our f prime at t column. So I just wanted to fill in a couple of values. There is some blue blanks that are worth filling in. And so, for example, if we wanted to fill in this blank, we would need to do some mathematics, right? And since this is the average rate of change column, also called the velocity, the average velocity, like this value here in the blank would be, because it's in the first column to the right of the function or the position function, we can just kind of recall that this is our f of t plus h minus f of t divided by h. This is what we're trying to do in this column. And we're going to use particularly the data from the function f, which is this first column. Okay, so we're going to do the function evaluated at, since we're trying to fill in this blank, my function, my value of t is equal to 1. So I'm going to do half a second ahead of 1, so 1.5, the function at 1.5, minus the function evaluated at 1, which is 1, and then I'm going to divide by the spacing between the two. So that would be 1.25 divided by 0.5, and we can see that when we do that quantity, you can see what's going to happen, that we get 1.25, let me go to my calculator here, 1.25 divided by 0.5, we get 2.5, which is the quantity that is given right here, 2.5. Okay, so if you want to fill in this blank right here, okay, we need to do different values, right? We need to do the function evaluated at 2 minus the function evaluated at 1.5 over the time spacing again, which is 0.5. So the function evaluated at 2 is equal to 4. The function evaluated at 1.5 is 2.25 over 0.5. So that would be 4 minus 2.25, and then we're going to divide all of that by 0.5. And this is where we started the course, the very beginning of the course at, and then you get 3.5 for the answer there. Okay, and you could fill in this other blank. You should try that one and see what happens. Okay, the next thing I want to do is to talk about the blanks that are in this column right here. There is a rate of change to the rate of change. Okay, and that rate of change to the rate of change, okay, is what we're going to call our second derivative. The average rate of change to the average rate of change, this is our velocity. The average rate of change to the average rate of change is what we call the acceleration. Okay, and it is the graph that we can see right here in this plot, that it is flat. Okay, so let's see if that makes sense from our picture. Okay, if I wanted to fill in, for example, this blank right here, notice that it is in the third column. So what we're trying to do is to compute the average rate of change. We're talking about doing the average rate of change to the data that's in the column next to it. Okay, so the average rate of change to the average rate of change, I need to look at the velocity right here. If I'm going to compute this quantity, I need the velocity at 2.5 minus the velocity at 2, and then I need to divide by the time spacing between them. The velocity at 2.5 is 5.5. The velocity evaluated at 2 is 4.5, and then we're going to divide by 0.5. And that will be 1 divided by 0.5, which is equal to 2. So the quantity that goes right here is equal to 2, and we can see that, in fact, every time you compute an average rate of change to an average rate of change for the t squared function, that you're always going to get 2 in this last column here. Okay? And what this is a reflection of is the fact that when you take the second derivative of the function t squared, you get equal to 2. Okay, so this is just kind of getting us back in the swing of things when it comes to the function and its derivative. And just to show you in terms of a table of values, okay, and if, for example, you wanted to create that table of values yourself, you could do, for example, 0.5, 1, 1.5, then you could use Excel or whatever your favorite method of computing a spreadsheet is. So then I'm going to put a formula. I'm going to take this time and I'm going to square it because we're squaring function. Okay, and we're going to get all of our time values. And then our velocity, how would we do that? We're going to take the position ahead minus the position behind. Okay. And then we will divide by the time spacing, which in this case is 0.5. And we can do that for some other of the values. And now we'd like to compute the average rate of change to the average rate of change, called the acceleration. And the way to do that would be to compute equal to the column before it, which is the velocity. So we're trying to look at the change in the velocity minus the velocity before it. Oops, sorry about that. Need to put my parentheses and then divide by 0.5. Okay, and you can see that that's 2. And in fact, if you compute other rates of change to the velocity, you're always going to get 2. Okay. And in terms of a picture, what we're seeing here is that as we move the value around, the red dot is the velocity, and the red arrow is the slope of the tangent line, and we can see that our number 2.21 here is the slope of the tangent line, and that's why our red graph is at about 2.21. Now, if you looked at the slope of the tangent line to the red graph, the rate of change of the rate of change, the red line has a tangent line that is always slope 2, which is why we're seeing the acceleration, the brown dot there, always being a 2 value, because the rate of change to the rate of change is a constant. So ends this first video, getting us back in the swing of things when it comes to graphs, velocities, first derivatives, second derivatives, and tables of values.